The body fluid compartments, extracellular and intracellular fluids. Textbooks. Guyton and Hall. Textbook of Medical Physiology. 11th edition. Pages 469 to 482. Textbooks. Guyton and Hall. Textbook of Medical Physiology. A South Asian edition. 2013. Pages 309 to 482. Judith beheading Holofernes is a painting of the biblical episode by Caravaggio, painted in c. 1598 to 1599 or 1602, in which the widow Judith stayed with the Assyrian general Holofernes in his tent after a banquet, then decapitated him after he passed out drunk. Of course, Judith did not think about the blood loss of the enemy. But surgeons always think about the amount of blood lost during operations. But how to determine the volume of blood circulating in a person? You can't do that in humans, but if I drain all the blood out of a cow and measure the volume of that blood, can I say that's the volume of blood that circulated in the animal's body? Of course not. Compensatory reactions will significantly alter the volume of circulating blood. Measurement of fluid volumes in the different body fluid compartments. The indicator dilution principle. The volume of a fluid compartment in the body can be measured by placing an indicator substance in the compartment, allowing it to disperse evenly throughout the compartment's fluid, and then analyzing the extent to which the substance becomes diluted. Figure shows this indicator dilution method of measuring the volume of a fluid compartment, which is based on the principle of conservation of mass. This means that the total mass of a substance after dispersion in the fluid compartment will be the same as the total mass injected into the compartment. This slide can be stopped and read what has been said above. In the example shown in figure, a small amount of dye or other substance contained in the syringe is injected into a chamber, and the substance is allowed to disperse throughout the chamber until it becomes mixed in equal concentrations in all areas. Then a sample of fluid containing the dispersed substance is removed and the concentration is analyzed chemically, photoelectrically, or by other means. If none of the substance leaks out of the compartment, the total mass of substance in the compartment, volume B multiplied by concentration B, will equal the total mass of the substance injected, volume A multiplied by concentration A. This slide can be stopped and read what has been said above. By simple rearrangement of the equation, one can calculate the unknown volume of chamber B. Note that all one needs to know for this calculation is 1. The total amount of substance injected into the chamber, the numerator of the equation, and 2. The concentration of the fluid in the chamber after the substance has been dispersed, the denominator. For example, if 1 milliliter of a solution containing 10 mg per milliliter of dye is dispersed into chamber B and the null concentration in the chamber is 0.01 mg for each milliliter of fluid, the unknown volume of the chamber can be calculated as follows. This method can be used to measure the volume of virtually any compartment in the body as long as 1. The indicator disperses evenly throughout the compartment, 2. The indicator disperses only in the compartment that is being measured, and 3. The indicator is not metabolized or excreted. Measurement of fluid volumes in the different body fluid compartments. The indicator dilution principle. Several substances can be used to measure the volume of each of the different body fluids. Measurement of total body water, TBW. Radioactive water, tritium, or heavy water, deuterium, can be used to measure total body water. These forms of water mix with the total body water within a few hours after being injected into the blood, and the dilution principle can be used to calculate total body water. Measurement of total body water, TBW. Another substance that has been used to measure total body water is antipyrin, which is very lipid soluble and can rapidly penetrate cell membranes and distribute itself uniformly throughout the intracellular and extracellular compartments. Measurement of extracellular fluid volume. The volume of extracellular fluid can be estimated using any of several substances that disperse in the plasma and interstitial fluid but do not readily permeate the cell membrane. They include radioactive sodium, radioactive chloride, radioactive iethylamate, thiosulfate ion, and inulin. When any one of these substances is injected into the blood, it usually disperses almost completely throughout the extracellular fluid within 30 to 60 minutes. Measurement of extracellular fluid volume. Some of these substances, however, such as sodium, inulin may diffuse into the cells in small amounts. Therefore one frequently speaks of the sodium space or the inulin space, instead of calling the measurement the true extracellular UID volume. Calculation of intracellular volume. The intracellular volume cannot be measured directly. However, it can be calculated as intracellular volume is total body water minus extracellular volume. Calculation of interstitial fluid volume. Interstitial UID volume cannot be measured directly, but it can be calculated as interstitial UID volume is extracellular UID volume minus plasma volume. Measurement of blood volume. If one measures plasma volume using the methods described earlier, blood volume can also be calculated if one knows the hematocrit, the fraction of the total blood volume composed of cells, using the following equation. For example, if plasma volume is 3 liters and hematocrit is 0.40, total blood volume would be 5 liters. Another way to measure blood volume is to inject into the circulation red blood cells that have been labeled with radioactive material. After these mix in the circulation, the radioactivity of a mixed blood sample can be measured and the total blood volume can be calculated using the dilution principle. A substance frequently used to label the red blood cells is radioactive chromium, 51Cr, which binds tightly with the red blood cells. The gold standard remains the measurement of whole blood volume with 51 chromium labeled red cells and the calculation of red blood cell and plasma volumes with the result of microhematocrit. In some cases, the direct measurement of plasma volume is performed with 125 iodine human serum albumin. Another method of determining total body water percentage, TBW%, is via bioelectrical impedance analysis, BIA. In the traditional BIA method, a person lies on a cot and spot electrodes are placed on the hands and bare feet. Electrolyte gel is applied first, and then a weak current of frequency 50 kHz is introduced. This AC waveform allows the creation of a current inside the body via the very capacitive skin without causing a DC flow or burns, and limited in the 20 mA range current for safety. Examples of commercial bioelectrical impedance analysis. Bioelectrical impedance analysis, BIA, actually determines the electrical impedance, or opposition to the flow of an electric current through body tissues, which can then be used to estimate total body water, TBW, which can be used to estimate fat-free body mass and, by difference with body weight, body fat.